Hello everyone, I'm Dr. Engineering. Welcome back to the VHDL tutorial series. Last time, we built a 4-bit ripple carry adder by manually copying and connecting 4 full adders. But what if we want to build a 16-bit or even a 128-bit adder? Would you still copy and paste all those full adders? Of course not. Today, I'll show you how to use for loops and generate statements in VHDL to simplify this process. By the end of this video, you'll have a much more efficient way to design larger circuits. Before we jump in, here's what you'll need. A computer, obviously. FPGA-related software. You can use any FPGA software, as long as it can build VHDL code and run simulations for your design. For this tutorial, we will use Vivado. If you want to use Vivado but don't know how to install it, you can go to my channel, find the related video. Third is some basic knowledge of digital logic in VHDL, but don't worry, I'll guide you through the entire process step by step. Now, let's talk about the for loop and generate in VHDL. These are powerful tools that allow us to automate repetitive tasks in our designs. Instead of manually defining each full adder and its connections, we can write a concise block of code that the synthesizer will expand automatically. This will save us a lot of time and reduce errors in larger designs. So, what exactly is a for loop in VHDL? Well, a for loop is used when you want to repeat a specific operation multiple times, based on a range of values. The syntax is straightforward: for parameter in range loop, followed by the statement that you want to repeat. And of course, it closes with end loop. In the example shown here, we have a for loop that runs 4 times, from I equals 0 to I equals 3. The loop statement says, for each iteration, assign the value of r underscore I to w underscore o. So, on the first iteration, I equals 0, r underscore I 0 will be assigned to w underscore o 0. On the second iteration, I equals 1, r underscore I 1 will be assigned to w underscore o 1, and so on, until I equals 3. What's really powerful about the for loop is that it allows you to scale your code without having to manually write each operation. This is incredibly useful in digital design when you're working with buses or large datasets. Instead of defining each individual signal assignment one by one, we can loop through them automatically. This not only saves time but also makes your code much cleaner and easier to read. So, if you're building larger systems or working with multiple signals, for loops can make your life a whole lot easier. Now that we understand the basics of the for loop, let's take it one step further with something called the for and generate loop. This combination is even more powerful when it comes to VHDL design. In VHDL, the generate statement is used when you want to create multiple instances of a component or a block of logic. The syntax is similar to the for loop, but with a generate keyword at the end. Here's how it works. The label gen in this example represents the name of the loop. Inside the loop, we are generating 4 instances of a module, named module underscore I. The loop runs from I equals 0 to I equals 3, and for each iteration, it maps the inputs and outputs of the module to different signal values in and out. Think of it this way: each generate loop creates a new module instance, and automatically connects it to a different part of the design based on the loop index I. In the example diagram below, you can see that we are creating 4 modules, module 0, module 1, module 2, and module 3, each connected to its respective signals. The beauty of this approach is that it allows you to easily replicate complex hardware components without having to write repetitive code. Just like in our ripple carry adder from the previous lesson, where we had to manually connect each full adder, now, with for and generate, we can automatically generate multiple adders, dramatically simplifying the process. This is perfect for scaling your designs to more bits, like building a 16-bit or 32-bit adder with minimal effort. As you can see, for and generate loops are a crucial tool in any VHDL designer's toolkit. Let's move to Vivado and implement this design step by step. First, open the ripple carry adder project that we created in the previous episode in Vivado. In the Sources tab, open the VHDL file of the circuit. To make our ripple carry adder more scalable, we'll define a generic variable in the initial entity declaration. Now, what is a generic variable? A generic is used to pass parameters from outside a module, such as an entity or architecture, to make the design more flexible. When designing a clock signal, we use constant to define the clock period. The clock period is fixed and cannot be changed. However, the value defined by a generic can be changed during the design process as needed. Here, we define G_bits to represent the bit width of our ripple carry adder, and in this case, we declare it as a 4-bit generic. Now, what does it mean when we say the G_bits is of type natural? In VHDL, natural is a predefined data type that represents non-negative integers starting from 0. By declaring G_bits as natural, we ensure that it will only take on non-negative values, which makes sense since the number of bits cannot be negative. Next, we'll simplify the declaration of multiple full adders. As we can see, the port mapping of each full adder follows a regular pattern, except for the first one, where the carry-in input is different from the others. To simplify the overall design, we'll make a small change to the W_carry signal. We'll connect the first bit of W_carry to the input of the first full adder, as shown in the diagram. Similarly, for each subsequent full adder, we modify the carry-in connections accordingly. Based on this new schematic, we can now use a for loop and generate statement to define multiple full adders. First, we'll comment out the previous full adder declarations. Then, we'll copy down the parts we'll still need. Using the forGenerate syntax that we just introduced, we define the label as set_fa, which represents that we are defining multiple full adders here. We also use I as an intermediate variable. Following the generate template, we assign a name to each full adder, fa_i, and keep the rest of the design similar to before. Some textbooks suggest declaring the submodules used in the architecture by first defining them as components, but here, I directly use the work library to declare the submodules. So, which method is correct? Actually, both methods are valid. Before VHDL 2008, using component was a very common approach. You'll even find a lot of VHDL open source projects where component is still used. This method was widely used in early VHDL designs because it clearly shows the interface structure when calling submodules, which is especially helpful in large-scale designs. After VHDL 2008, we can directly use the work library to instantiate submodules. The work library is automatically generated when we create a VHDL project. Once we add the full adder design file, the full_adder entity can be used directly. This method is called direct entity instantiation, and it's simpler and more convenient. Now, back to our design. We'll use the work library method to complete the forGenerate part. Based on the updated schematic, we modify the internal connections like this. Also, for the input to the first full adder, although we represent it with W_carry 0, we still need to map it to the input interface of the ripple carry adder, specifically to the I_cin defined here. Finally, for the output, we need to make the corresponding changes to the highest bit of W_carry. And we also adjust the bit width of W_carry. Once everything looks correct, if there are no syntax errors, we'll get a green light here. It's just like a traffic light. If there's any syntax error, we'll get a red light, and we won't be able to proceed. Now it's green, so let's move on. We'll run the simulation. The test bench is the same as last time. So let's look at the simulation waveform. Again, we'll click Zoom Fit and adjust the values to assign decimal. Now we can see that the ripple carry adder works as expected, adding A and B to produce the result. This shows that our new design works just as well as the previous one, but with far less effort. In addition, we had a question left over from the last session: if CIN is 1, how much will the final result increase? Let's go back to the test bench and set all the CIN inputs to 1. You only need to change it once at the beginning. After verifying everything, save the changes and run the simulation again. You'll be prompted to reload the design files. Click Yes. Then, when asked whether to save the previous run files, we don't need them, so click Discard. Again, we'll adjust the window to fit and change the value format to assign decimal. Now, we can see that the final result adds A, B, and CIN together. This aligns with our initial input-output model for the ripple carry adder. Since all three inputs, A, B, and CIN, hold equal importance, CIN only affects the least significant bit, LSB, of the result, meaning it will add 1 if CIN is 1. Before we wrap up, I encourage you to try implementing this on your own. Design a ripple carry adder for 8 bits or even 16 bits using the generate method we learned today. Leave a comment to share your experience or any challenges you faced. Don't forget to like this video, subscribe, and check out my other tutorials for more FPGA and VHDL learning. That's all for today. Practice makes perfect, so keep experimenting and soon you'll become FPGA experts. See you in the next video.